Morning, one and all. Myself, Dr. Divya. Today we are going to talk about the molecular orbital theory. This molecular orbital theory was first proposed, is also called the Hund and Mulliken because the Hund has proposed a molecular theory, and along with him, Mulliken, John Slater, Johns, all Leonard Johns, all of them worked on this molecular orbital theory. On after the names of these scientists, molecular orbital theory was also named as a Hund-Mulliken theory. Before getting into the postulates of molecular orbital theory, let me explain what is constructive interference and destructive interference because the constructive interference and destructive interference idea must be there to understand the postulates of this molecular orbital theory. I think you people are all familiar with the wave nature and the particle nature of the electron. If we consider only the wave nature of the electron, um, let us say this is the wave nature. This is a wave nature of one electron, and this represents the wave nature of the other electron. Okay, this is called the crest, and this is called the trough. If the crest of one electron and the overlaps with the crest of another electron, it results in the formation of a constructive interference. Similarly, if the crest of one electron and the trough of another electron overlap with each other, it results in the form of a destructive interference. It is the constructive interference, destructive interference. It's nothing but the constructive interference is formed by the overlapping of crust of the two electrons if wave nature is considered. Okay, now the destructive interference is formed when the crust of one electron and the trough of one electron overlaps, resulting in formation of destructive interference. Now, the main features of the molecular orbital theory is first, these postulates can be understood by taking the example of this one. Here, S it is represented as a representing S orbital of one atom, and this is a S orbital of another atom. This is a blue color represents one atom, and this pink color represents another atom. Let us take up the example of hydrogen itself. This is a 1s orbital of one hydrogen atom, and this is a 1s orbital of another hydrogen atom. When these are considered, these are called the atomic orbitals. These are nothing but atomic orbitals. Okay, the atomic orbitals of the two combining atoms overlap to form molecular orbitals. Okay, they see here, this can be clearly understood. As per molecular orbital theory, the atomic orbitals of one electron overlaps with the atomic orbital of another electron. Here, this one and this one, they are overlapping in form, they are overlapping with each other, and they result in the formation of these molecular orbitals. Okay, this is the first postulate. The atomic orbitals of the combining atoms overlap to form molecular orbitals. Hence, as a result, the atomic orbitals lose their individual identity. Thus, in molecular orbitals, the electrons revolve in the field of more than one nucleus. Here, the electrons that are present will have more, will move in a field having more than one nucleus. Here, the black dots represents the nucleus. So, the electrons will have more than one nucleus when molecular orbitals are formed. The second feature is the number of molecular orbitals combined will be equal to the number of molecular orbitals formed. Okay, here see the number here two atomic orbitals are combining. So here two molecular orbitals are formed. If at all three molecular orbitals combine, then three molecular orbitals will be formed. So the number of molecular orbitals formed will be equal to the number of overlapping atomic orbitals. The maximum capacity of the molecular orbitals is 2 electrons with opposite spin. This can be better understood by this. Here, you see, this is a 1s orbital of hydrogen atom, and this is a 1s orbital of another hydrogen atom. Hydrogen atom will be having only one electron. Okay, so these two hydrogen atoms combine to form two molecular orbitals. Okay, this is one molecular orbital and this is another molecular orbital. As we're talking about the electrons, the maximum capacity of the molecular orbitals is 2 electrons with opposite spin. These molecular orbitals can hold this molecular orbital can hold 2 electrons. This molecular orbital can hold 2 electrons and this molecular orbital can hold 2 electrons, and the 2 electrons will be of opposite spin. Only those atomic orbitals can combine to form molecular orbitals which have comparable energies. Okay, comparable energies means, see for example, the 1s orbital will combine with the 1s orbital. But similarly, the 2x orbital can combine with the, 2px orbital can combine with the 2px orbital. Okay, similarly, 2py orbital can combine with the 2py orbital of another atom. Okay, two atoms here representing. This statement says that the 2px orbital cannot overlap with the 2py and 2pz orbitals. Once again, I repeat this postulate. Only those atomic orbitals can combine to form molecular orbitals which have comparable energies as well as proper orientations. This is the very important postulate. Next, the molecular orbitals formed. As per LC theory, the linear combination of the atomic orbitals can either take place by constructive overlap or destructive overlap. Okay, if the constructive overlapping takes place, it results in the formation of bonding molecular orbitals. If the destructive overlap takes place, it results in the formation of anti-bonding molecular orbitals. Okay, this is a bonding molecular orbital and this is anti-bonding molecular orbital. Here, the constructive interference of the atomic orbitals have taken place, resulting in formation of bonding molecular orbital. Here, the destructive interference of the atomic orbitals have taken place. Destructive interference has taken place and it has resulted in the formation of anti-bonding molecular orbitals. The bonding molecular orbitals are represented by sigma, pi, delta, etc. And the anti-bonding molecular orbitals are represented as sigma star, pi star, delta star, etc. Okay, depending on the type of interference, the molecular orbitals are given the names as sigma, pi, delta, sigma star, pi star, delta star, like that the names were given. Now, talking about the characteristics of the bonding molecular orbitals, these bonding molecular see here, the bonding molecular orbital is represented as sigma, and here the anti-bonding molecular orbital is represented as sigma star, because here 1s orbital and the one hydrogen atom and the 1s orbital of another hydrogen atom has undergone destructive interference and result in the formation of anti-bonding molecular orbital. As talking about the characteristics of this bonding molecular orbital, it possesses high electron density in the region between the two nuclei. Let me show this one. Yes. See here, the bonding molecular, or this is the bonding molecular orbital and this is anti-bonding molecular orbital. Okay, in bonding, talking about the bonding molecular orbital, this bonding molecular orbital will possess high electron density. Here, the electron density will be very high. This is here means it is the region between the two nuclei of the molecular orbital. Okay, talking about the anti-bonding molecular orbital, it possesses a low electron density in the region between the two nuclei. Here, it is a region between the two nuclei, and the probability of finding the electron in this region is very less. The electron density will be very low. So this region is called the nodal plane. Nodal plane is nothing but the place or the plane where the probability of finding electron is zero or very less. So this region is called nodal plane, and nodal plane is generally found in anti-bonding molecular orbitals. Coming to the bonding molecular orbitals, the density will be very high in the region between the two nuclei, and in anti-bonding molecular orbitals, the density of the electrons between is very low in the region between the two nuclei. So, because the electron density is very high over here, this bonding molecular orbital will impart stability to the electron. It means the energy of the bonding molecular orbital will be very less. And coming to the anti-bonding molecular orbital, it imparts instability to the electron. Okay. Now, talking about bonding molecular orbital, every electron in it makes contribution to the attraction of the two combining. Every electron in this make contribution to the. Sorry. Talking about the bonding molecular orbital, every electron in it makes a contribution to the attraction of two combining atoms, and it is also formed when the lobes of the combining atomic orbitals possesses the same sign. Just a second. Here, see. Here, these are the combining atomic orbitals. I'm talking about the bonding molecular orbitals. If the combining atomic orbitals possesses the same sign, then then obviously bonding molecular orbitals are formed, and thus the electrons will help for the attraction of the two atoms. Here, the two atoms have combined, and almost it's like this. Here, the attraction is very high. Talking about the anti-bonding molecular orbital, the every electron in it makes contribution to the repulsion of the two combining atoms. See here, you can see the repulsion, the electron density is high over here. Already I told you the electron density will be very less in the region between the nuclei. Okay, here there will be nuclei, and here this will be nuclei. Actually, these signs doesn't represent the nuclei. These signs are given just to make you understand that this is a constructive interference and destructive interference. Please don't misunderstand these signs for the nucleus. Okay. Now, talking about the anti-bonding molecular orbital, every electron in it makes contribution to the repulsion of the two combining atoms. The anti-bonding molecular orbital is formed when the lobes of the combining atomic orbitals possesses when the lobes of the combining atomic orbital possesses different signs. Okay, these are the characteristics of bonding molecular orbital and anti-bonding molecular orbital. Here, this slide shows that in which situations a sigma bond is formed, and in which situations sigma is formed, and in which situations pi type molecular orbitals are formed. The sigma molecular orbitals are formed for s orbitals. One s orbital combined with one s orbital and results in the formation of sigma bonds. Similarly, the 2pz and the 2pz of one atom combined with the 2pz of another atom, it results in the formation of one bonding and one anti-bonding molecular orbital, because two atomic orbitals are involved. If two, if here the 2pz orbitals will result in formation of sigma bond. If 2px orbitals combine, then the molecular orbitals are represented by pi. If it is bonding, it is represented as pi, and if it is anti-bonding, it is represented as pi star. Similarly, if 2py orbitals are combined, then it results in then the molecular orbitals formed are also represented by pi. But here they are represented as 2py, I mean pi 2py, and here they are represented as sigma, pi star 2py. Okay, overall, if s orbitals combine, sigma. If pz orbitals combine, the molecular orbitals are represented by sigma. If px orbitals combine, the molecular orbitals are represented as pi, and even for 2py orbitals also, I mean py orbitals also, the molecular orbitals are also represented by pi. Okay, these are the postulates of molecular orbital theory. Yes, the molecular orbital theory also tells about the filling up of the electrons. Okay, this slide represents the nothing but the whole overall explanation of the previous slide. So here one s orbital and another s orbital combine means undergo constructive interference resulting in formation of bonding molecular orbital, and one s orbital of another atom undergoes destructive interference with the one s orbital of another atom, and it results in the formation of antibonding molecular orbital. Here, subtraction of orbitals results in low electron density in the overlap region, which is nothing but the nodal plane. Now, the filling of yes, the filling of the molecular orbitals means filling in the sense these are the molecular here the molecular orbitals are represented as lines. Okay, when the filling of these molecular orbitals filling mean the sense filling of the molecular orbitals with electrons will follow the Aufbau's principle, Pauli's exclusion principle, and Hund's rule. These three rules are followed by the electrons of the molecular orbital while filling up of the molecular orbitals, the electrons will follow these rules. Okay. Hmm. Now, uh, see, this actually the electronic config. This is nothing but the electronic configuration of the molecular orbitals formed. Actually, the molecules are formed by the combination of the atoms. If, for example, from hydrogen to from hydrogen to nitrogen, if the atoms combine to form molecular orbitals, means for lithium atom, beryllium atom, boron atom, I'm sorry, no, for lithium molecules, beryllium molecules, boron molecules, carbon molecules, and nitrogen molecules, if the molecular orbitals formed, this will be the electronic configuration. Okay, means the electrons filling will follow this order. First, 1s orbital, sigma 1s orbital is filled, then sigma star means antibonding 1s orbital is filled, and next sigma 2s, sigma star 2s, and then pi 2px and pi 2py. These two orbitals are degenerate. Already I told you, if for py and px the molecular orbitals are represented by the pi bond, and for pz it is represented as sigma. These two orbitals will be degenerate in nature, so they are represented as equal. Okay, after this sigma 2 pz, and then pi star 2 px and pi star 2 py, the antibonding molecular orbitals will also be of equal energy. Next comes the sigma star 2pz. This order is followed. This is nothing but the increasing order of energy of various molecular orbitals for from lithium to nitrogen. I mean hydrogen to nitrogen. Next, from oxygen onwards, from oxygen molecule onwards, the order will be changed. Here you see till here it is the same. Still sigma star 2s, the order is same. But coming to the oxygen means the molecules from oxygen. First, sigma 2pz orbital, the filling of the electron will take place from sigma 2pz orbital, means the energy of the sigma 2pz orbital will be less when compared with the pi 2px and pi 2py orbital. When we see here, the energy of the pi 2px orbital and pi 2py orbital is less when compared with the 2pz orbital, but it is completely reverse for the molecules from oxygen. And the reason for this is this is because in case of oxygen, fluorine and neon, the difference in energies between 2s and 2p atomic energy levels is very large. As a result, the energy levels of sigma 2s molecular orbital and sigma star 2p molecular orbital are so close that the repulsive forces operate between the electrons present in them and raises the energy level of the 2p pi 2p molecular orbital above that of sigma 2s molecular orbital. Because of these repulsive forces, the stability or the energy of the molecular orbitals is reversed from oxygen to from oxygen onwards, the molecular orbital's stability is reversed. The difference will be seen only in case of pi 2p pi bonding and anti-bonding molecular orbitals of 2px, 2py, and 2pz. This has to be kept in mind because it's very important. Next comes the, already I told you, the while filling up of the electrons will follow Afbo's principle, Pauli's exclusion principle, and Hund's rule. Talking about the stability of the molecule here, the electrons will be filled up in the molecular and anti-bonding molecular orbitals. Already in the previous slide I have shown you here these two electrons. For example, these two electrons will become the electrons of the bonding molecular orbital, and if electrons are present here, the electrons that are present here will be represented as anti-bonding electrons. Here these electrons are represented as Na, means sorry, Nb means bonding electrons, number of bonding electrons, and the electrons that are present in this antibonding molecular orbital are represented as Na. See, if the if the bonding electrons, number of bonding electrons are greater than number of anti-bonding electrons, then the molecule is said to be stable. If the number of bonding electrons are less than anti-bonding electrons, or number of bonding electrons are equal to the number of anti-bonding electrons, then the molecule is said to be, sorry, actually it is said to be unstable. It is not stable, it's written wrong. Okay, here Nb represents, if Nb is greater than Na, the molecule is said to be stable. If Nb is less than Na or Nb is equal to Na, then it is said to be unstable. Nb is nothing but the number of electrons occupying the bonding molecular orbital, and Na is nothing but the number of electrons occupying the anti-bonding molecular orbitals. The next comes the bond order. We can calculate the bond order using these number of bonding and anti-bonding molecular orbitals. The bond order of a molecule is nothing but the measurement of the strength of bond between the two atoms, and it can be calculated mathematically as the bond order is equal to half into Nb minus Na. Nb and Na are nothing but number of bonding electrons and number of anti-bonding electrons. If the after calculation, if the bond order obtained is 1, then it indicates that single bond is formed. If the bond order is 2, it indicates that double bond is present. If bond order is 3, it indicates that triple bond is present. And this one I think you people know, the bond order is nothing but inverse of the bond length. With the help of this molecular orbital theory, we can also predict the magnetic nature of the a molecule. All the molecular orbitals are doubly occupied, then they are said to be diamagnetic in nature. If all the molecular orbitals are singly occupied, if not all molecular orbitals, even if one molecular orbital is singly occupied, then we call it a then we call that the molecule is paramagnetic in nature. Instead of using the word all molecular orbitals, it's better to say that the valence molecular orbitals. Now, this represents the molecular orbital diagram for lithium, beryllium, boron, carbon, and nitrogen. From oxygen onwards, the molecular orbital diagram will be different. If you see here, in this part, there will be difference between these and the where there will be difference. Just go to the next slide. Yes, here if you see from oxygen on, here if you see from oxygen onwards, the energy, see pi 2px is represented here, and pi 2px and 2py are here. Coming to the previous slide here, pi 2px and pi 2py are represented at lower energy when compared to the sigma 2pz. This is the only difference, and again coming to the antibonding molecular orbital, it remains the same. Here see pi 2p, pi star 2px and pi star 2py, then sigma star 2px. Same holds good for the molecules from oxygen also. Here they are represented as the same. Only this region will differ because of the repulsive forces. This represents the electron fielding of the nitrogen molecule. Here you see these are the bonding electrons, these are anti-bonding electrons, these are again bonding electrons, these are anti-bonding electrons. Here the bonding electrons, and if electrons are present in this three molecular orbitals, they will become the anti-bonding electrons. If you go for the nitrogen molecule, the bonding electrons are 10. See 1 2 3 4 5 6 7 8 9 10. If we count the antibonding electrons, 1 2 3 4 5 and 6 only. I'm sorry. Okay, sorry, these are bonding electrons. No, here antibonding electrons are not there. Only 4 antibonding electrons are present. So it's represents half into 10 minus 4. It is the bond order for the nitrogen molecule you obtained is 3. So as 3 bond order is 3, already I told it, it represents that the nature of bonding is triple bond. And also see, if you see the electrons, no unpaired, no orbital is with unpaired electron, means it is diamagnetic in nature. Even if one electron is present here, this will become paramagnetic in nature. This represents a molecular orbital diagram for the oxygen. Here you can see, here it has followed the rules. Once as both these orbitals are degenerate, first these orbitals are filled with one electron, and then the pairing will happen. The degenerate orbitals will occupy each electron first. They won't undergo pairing at first. So here, two electrons are present, and also these, as these electrons are unpaired, the oxygen molecule has become paramagnetic in nature. This is the molecular orbital diagram for fluorine. Here the bond order obtained is 1, and so the nature of bonding has become single bond, and F2 molecule has become diamagnetic in nature because there are no orbitals with single electrons. All of them are paired. Thank you. By this, the molecular orbital theory has completed. Thanks for participating.